Good morning, ladies and gentlemen. Today we're looking at an application of integration, and this particular application is finding the area between two curves. So here we have a pair of curves, taken straight from the textbook, where we have an upper curve, the blue line that I'm highlighting now, and a lower curve here, and we see that there's an area formed between them. Now, to find the area of this, we know that if we can find the area under a curve, so if we go under a curve and then we find the area under the other curve, basically what we can do is we can do the top curve's area under minus the bottom curve's area under, and what we get is the area enclosed between the two of them. So, and the great news is this works even if the bottom curve dips below the x-axis, because for that portion the area appears negative, but the double negative adds that area on to the sum of the two areas. So the formula for us is, if we want to find the area between two curves, we say it's the integral of a to b, a and b meaning the intersection points, or where they meet, of f of x take g of x dx. Or, in terms of upper and lower function, you could go yu take yl. Now, quite an easy concept to understand. Let's look at how it works in maths. Say you find the area enclosed by y equals minus a half x squared plus 6 equals, and y equals a half x plus 3. Now you may be able to tell instinctively which one of those is the top function, you may not, so it certainly helps to have a look on a graph. If in doubt, graph it. There's its graph. Clearly the quadratic is on top. Next thing we need to do is find where our a and b points are, the intersection points. So we can go gsolve intersect. Now, I would expect you to be able to do this algebraically, but using a calculator in this instance is fine. Minus 3 and positive 2. So our intersect points are x equals minus 3 and positive 2. To find where these work algebraically, we solve simultaneously. And by solving simultaneously is both of these are equal to y, so therefore we can let them equal each other. Remember, we're aiming for that. Equals a half x plus 3. Where they intersect, the y values are the same, therefore the x values are the same, so if the y values are equal, we can make the x portions of the equation equal and then solve for x. From here, I would multiply by 2, minus x squared plus 12 equals x plus 6, and I would then bring everything to one side and put 0 on the other. 0 equals x squared plus x minus 6, then 0 equals factorize x plus 3, x take 2, you should be quite comfortable with that sum of product factorization, and that using null factor law gives us solutions of minus 3 and 2. Alright, so now we've got the intersection points. These form our a and our b. So we want to integrate, using a definite integral, from a to b of the upper take the lower, which looks like a half x squared plus 6, negative a half x squared plus 6, take the lower. Now the reason I'm being so careful with brackets is because this negative applies to both terms inside the brackets. And it would be quite a common error, especially if there's a negative in front of that 3, to forget to make the double negative, or in this case, forget to subtract. dx. Then, keep simplifying. A to b minus a half x squared minus a half x plus 3 dx. And really here, I don't need to be writing a to b anymore because it's from minus 3 to 2. And in fact, I'm not sure why I wrote a to b in the first place because we know it's from minus 3 to 2. Alright, and now it turns into a problem where, well, we've done these in the previous video, where we're looking at area under a curve. So it's very much simple of identifying the top function, the bottom function, intersect between the two, and then simplify. Now, that I won't go through, but you can do that pretty comfortably yourself. Here, two different equations. And clearly the linear is on top, and we're going to call that a type of exponentials on the bottom. So what we're going to do is go integral of 0 to 2 is not so bad. And then what we've got in the brackets is x plus 1 take x e to the minus x squared dx. Now, this is a little different from above, because up above, we had two things in the brackets here and here, which could be simplified quite nicely into polynomials, and then from there, really, we break it down into chunks and go on 1, 2, 3. However, here, we aren't really even looking at like terms. So what I would do is I would just split this up into chunks now. I'll go from 0 to 2 of x plus 1 minus x e to the minus x squared dx. And then keep going. And remember, this can be then written as integral of 0 to 2x dx plus integral of 0 to 2 of 1 dx minus the integral of 0 to 2x e to the minus x squared dx. Alright, and then we go on to integrate all of them by parts. Alright, so this first one here would be a half x squared, table brackets from 0 to 2 plus x from 0 to 2 minus, make sure you don't lose that sign, and strictly speaking you haven't been taught and don't have to know how to integrate this one, but you can sort of imagine that e to the minus x squared has come from another e to the minus x squared, so imagine differentiating. And then if you were going to differentiate this, it would throw out a minus 2x. However, there's only an x at the front, so how do we deal with the minus 2x? Well, we throw out minus a half. So if we throw out minus a half, and now imagine the minus 2x coming down, minus a half, as the minus 2x comes down, it would combine with the minus a half to make positive 1x, which is that there. And then 0 to 2. And from here, you can make the substitutions and do that fairly comfortably yourself. Alright. I don't want to spend too long on that one. This one I do want to spend a little while on. So, that one, fairly easy. You can do it similar strategy to above. If you're not sure, please ask me in class. This one here is different because we don't have a clear upper and a clear lower function. They change halfway through. So what we have to do is consider this in parts. We need to do here, I'm going to call this y1 and y2. We need to integrate from 0, and we can see the intersection, to pi on 4 of y1 take y2. So for that portion, dx, y1 is on top. And then we add on the next portion from pi on 4 to pi on 2, and this time it's y2 take y1 dx. Now, here this looks rather intimidating. Please don't try and take shortcuts with it. If you do it nice and systematically, it will work out nicely. So once again, you can go through and then simply make the substitutions for each of them, and you're going to go through finding area under the curve for all of them. And each of them you should be able to break down into chunks. So from 0 to pi on 4, it should be cos x take sin x dx, which would then go, I would take it in two parts. 0 to pi on 4 cos x take 0 to pi on 4 sin x dx, plus the next portion coming down, pi on 4 to pi on 2, y2 is sin x, take pi on 4 to pi on 2 cos x. And all of that is dx dx. And if you follow it through, it should come out with quite a neat result. Alright. And for my own amusement, I continued it through. Now, note, there's a few things or traps that are easy to fall into. Be very careful with all the negatives that get thrown out. So, you see this negative here, that has to stay a negative around the brackets, that is this. And that, remember, is minus cos of pi on 4 minus cos of the top minus cos of 0, which throws up a brutal little triple negative. Negative, negative makes a positive, then the negative from outside the bracket makes it negative again. And it's entirely possible I've made a mistake here, so please point one out if you can. Similarly here, there's that double negative thrown out by the minus cos, and so on. A couple of these drop out to 0, and what you get in the end is, well, minus 2 plus 4 on root 2 would probably let you have it at that. But if you want to simplify, you can go all the way down to there. Alright, thank you very much.